Hi folks! In this lecture, we will focus on physical changes of state for an ideal gas. When knowing 3 of the 4 variables, N, P, V, T, and the ideal gas equation of state, PV equals nRT, it's a straightforward task to define the current state of the gas system completely. Now we're going to change the state of the ideal gas and see if we can predict properties of the future state. It turns out that it just takes a little algebra. We will take an ideal gas and take it from an initial state 1 to a final state 2. Looking at the equation that defines an ideal gas, PV equals nRT, we see that there are 4 physical properties we can change in an ideal gas, though we don't have to change them all. These physical properties are pressure, volume, amount of gas in moles, and temperature. So, we can envision changing one or all of them in a process that moves it from state 1 to state 2. Now, we're going to use our PV equals nRT equation to derive a master equation that will help us in our computations. Let's first rearrange the equation of state to be R equals PV divided by NT. Since R is a fundamental constant of nature and cannot change, we can be assured that the ratio PV divided by NT is also a constant and will be the same for any state or condition of our ideal gas. What this means to us is that for any change in state of an ideal gas, the following equation will apply. P1 V1 divided by N1 T1 equals P2 V2 divided by N2 T2. This is our master equation for any change of state of an ideal gas. To use this equation for a change of state problem, we do the following. The first step is to identify what variables are not changing or being held constant in the process and eliminate them from the master equation. Here are a few famous cases where the scientists stumbled upon relationships before they even knew about atoms or moles or even had decent thermometers, let alone an absolute temperature scale. Boyle's law describes a change of state where the temperature and amount of material do not change. We drop the temperatures, all the T variables, and the amounts, the N variables, from the master equation, yielding a simpler equation, P1 V1 equals P2 V2. Under these conditions, we see that the pressure and volume are inversely related. For example, if the pressure increases in the process, volume will decrease. Others include Charles' law, which describes a change of state where the pressure and amount of gas is constant. Eliminating amounts and pressures from the master equation leads to the equation V1 divided by T1 equals V2 divided by T2. This equation emphasizes the direct relationship of volume and temperature under these conditions. So, if the temperature increases in a process, the volume will also increase in the process. Here's one we might already recognize. Avogadro's law describes a change of state where the pressure and temperature of the gas are held constant. Again, eliminating pressures and temperatures from the master equation leads to a simple equation, V1 divided by N1 equals V2 divided by N2. Avogadro's law is clear in the equation. There is a direct relationship between the volume and amount of gas at constant temperature and pressure conditions. Okay, the second step is to identify which quantity we're solving in the problem, and there will always be just one quantity that is unknown in the problem statement. To solve for more than one variable, we would need an additional information. Now, we will rearrange the equation from step 1 to solve for this unknown quantity. Make sure that the temperature is in Kelvin. Only absolute temperature scales work in our equations. And make sure the amount is in moles. So if you have the amount of matter in mass units, convert to moles utilizing formula weights. And make sure that all the volumes and pressures are in the same units, and then plug all the knowns into the equation and solve for the unknown. Let's demonstrate by doing a few ideal gas changes of state problems. Example 1. A sample of gas has an initial volume of 3.9 liters at a pressure of 705 torr. If the volume of the gas increases to 5.5 liters, what is the final pressure? Assume constant temperature and amount of gas. In this example, we assume that the amount of gas and the temperature are held constant. Let's try to predict the results. At constant temperature and amount, the volume should be inversely related to the pressure. As the volume increases from 3.9 to 5.5 liters, the pressure should decrease, so we expect a lower value than 705 torr. As we have shown, this problem is an example of Boyle's law, where we drop T and N from the master equation and get the equation to solve. P1V1 equals P2V2. The quantity we want is the final pressure, P2, so we rearrange the equation to solve for this quantity. P2 equals P1V1 divided by V2. We check to make sure the units of our volumes are the same. We then plug into the equation and calculate. Notice that the units on volume will cancel, leaving us with just torr, a pressure unit. Our final answer is 500 torr, which is smaller than the original pressure, just as we expected. Example 2. A 48 milliliter sample of gas in a balloon is warmed from 20 degrees C to 80 degrees C. What is the volume of the gas at the final temperature? In this example, we can assume the amount and the pressure are constant, leading to the equation V1 divided by T1 equals V2 divided by T2. This is an example of Charles' law. The final volume is unknown, so the equation rearranges to V2 equals T2 V1 divided by T1. Now, if we plug in the temperatures and volume, we will get the wrong answer. We have to remember to change the temperatures to Kelvin before plugging into the equation. Our final answer will be 57.8 milliliters, which makes sense because gases in these conditions would expand like a hot air balloon when you heat them up. Let's do one final example where a lot of physical properties are changing. Example 3. A sample of gas with an initial volume of 28.5 liters at a pressure of 0.954 atmospheres and a temperature of 89.6 degrees Fahrenheit is compressed to a volume of 3.91 gallons and warmed to a temperature of 102 degrees Celsius. What is the final pressure of the gas in pascals? The only thing we can assume is being held constant this time is the amount of gas, leading to the equation P1V1 divided by T1 equals P2V2 divided by T2. The quantity we want to solve for is P2, which we also want in pascals. So P2 equals P1V1T1 divided by T1V2. The temperatures need to be converted to Kelvin first. For volumes, we need to decide on one unit, either liters or gallons. Let's go with liters and convert our second volume from gallons to liters. We want the pressure in pascals, so we will convert our original pressure to pascals. Again, remember not to round off too early. We do that at the end. Plugging this all in, we get 3.28 times 10 to the 6 pascals, which is about 32.4 atmospheres if we convert back to atmospheres to compare the answer to the initial pressure. The pressure dramatically increased. Okay, that gives us a good handle on ideal gas changes of state. We still have a few different physical changes to explore, so keep on working the lectures. Catch you soon.